Good morning, everyone. This is Michael Dong, and here's in episode number 5 on the best practices in the selection and operation of reverse phase mobile phase. This is my agenda. The first is on mobile phase preparation, premixing, filtration, and degassing. Next topic is reverse phase mobile phase, is best practices and also trends. And we will touch upon several topics, including the use of balanced absorbance mobile phases, high pH mobile phase and when to use, how to avoid ghost peaks, and some comments on reagent quality and mobile phase shelf life. And number 4, why and how to replace TFA, trifluoroacetic acid, for LCMS of proteins and peptides. And finally, other topics of interest, such as ion pairing reagents, the use of chaotropic reagents, the use of phosphoric acid, and MTBE to replace THF. This slide discusses mobile phase preparation and the manual premixing for isocratic analysis. Premixing of the mobile phase can be used for isocratic analysis, and why manual mixing is generally not preferred. To do premixing of mobile phase manually, the best way actually is just to measure the volume of each solvent separately in the measuring cylinder. You don't really need to or want to use a volumetric flask. And then you combine these solvents. Okay, the reason why you do it like this is the fact that solvents are generally not ideal solvents. As you mix water with methanol or acetonitrile, upon mixing, the solution either gain or lose heat. It gain heat in the case of methanol and lose heat in the case of acetonitrile, and then the mixture would get cooled down. So there actually a loss of 4% for methanol and loss of 2% when you mix acetonitrile water, respectively, due to the negative delta volume of mixing. So don't use a volumetric flask or pipette to make your premix solvent, and try to fill to volume QS with the other solvent, since in that case the order of mixing is really important, and you don't really get as accurate as that of a measuring cylinder. Generally, pump blending is much preferred, particularly with modern pumps, which are much more convenient. It's actually much more accurate. So modern pumps actually have really good composition accuracy, and it can automatically compensate for the delta volume of mixing and also of compressibility. However, one must do online degassing, which turned out to be mandatory. Next topic is mobile phase preparation. Big question is to filter or not to filter. Generally, mobile phase filtration is recommended by most manufacturers of equipments, although, in my opinion, it may not be totally necessary if certain conditions are followed. Okay, what do you do when you do filtration? To filter or aqueous buffer or ion pairing agent through these membrane filters. These are 0.45 or 0.5 micron membrane filter, typically made from these material. Nylon is preferred. On the right-hand side are the filtration apparatus, which is a vacuum filtration flask. You need a vacuum pump and a solvent trap to protect the pump. Make sure that you use thick wall flask and there's no cracks when you filter it. There's really no need to filter HPLC grade solvent you purchase because they have been pre-filtered. Or if you get your purified water through systems such as Millicube system in the laboratory, which are also filtered. Filtration may not be required for if you use high purity buffer. For instance, if you purchase ammonium formate, which is a very common buffer. You could get a high POV grade, which is 99.995% grade, LCMS grade from Sigma Aldrich. In those cases, you might not have to filter it. Now, the advocate for not filtering mobile phase may sound radical or even heretical in some cases, though most labs, including the lab that I've been involved with, have been operated without any problem by using high purity reagents and solvent, and basically just rely on the preventive maintenance, which is performed typically annually to replace the built-in filter in the HPLC system and pumps. For those of you interested to pursue that topic a little bit more further, there's this free article available on the 7 common fault parts in HPLC, published in 2014. The use of mobile phase degassing is definitely mandatory to give very high level composition and accuracy, either in premixing for isocratic analysis or for gradient. Now, traditionally or historically, degassing can be performed by stirring the solvent under a vacuum, but that really is not very effective. And also, if you leave it up to the atmosphere, it would regas after 4 hours. The next one is helium sparging pressurization. It is effective, however, it tends to be expensive and also not very convenient. So today, everyone basically use the online vacuum degassing, which is mandatory for accurate pump blending and for very highly reproducible gradient program. So that is universally adopted. That's the norm. Now, most of these degasser are shown here is a vacuum degasser schematic, which is basically the degassing is accomplished by passing solvent, typically 4 different lines, into the semi-permeable Teflon membrane, in which the air is being sucked out of the solvent using a vacuum pump. And so the amount of nitrogen and oxygen in the dissolved solvents, dissolving the solvent, are reduced tremendously. So modern degasser uses a semi-permeable Teflon membrane tubes, which are evacuated to reduce the level of air from 16 ppm, which is a bit too much, to less than 1 ppm. Okay, so this is to ensure that there's no outgassing during pump blending. So all modern degasser can be turned on all the time, meaning the pump is not intermittently operating, but on all the time. And these tubes, the semi-permeable tubes, have volume which are pretty small, which is less than 1 milliliters. So the pump should be kept on all the time. And very important to make sure that even though you're blending just A and B, that all 4 solvent lines should be filled with solvents to prevent the vacuum pump basically sucking air. So that's not really a good thing. So you should fill all the 4 lines with solvents. In this slide, we just mentioned how do you prepare a mobile phase, such as some simple mobile phases, 0.1% TFA or trifluoroacetic acid in 1 liter of water. So basically, it's very simple. You pipette 1 ml of high purity TFA into 1 liter of HPLC gray water. Basically, you can use one of these pipetters, Appendor pipetter, and also disposable tip. That's typically okay. And then you use HPLC gray water from such a millipore or millicube water. So the filtration of this simple mobile phase is not needed because the water is already purified and use a high-grade TFA. Next is the recipe to how to prepare a 20 millimolar ammonium formate at pH 3.8. It's one of the very common and very effective mass spec compatible mobile phase A for pharmaceutical analysis. Okay, so here's the procedure. Weigh 1.26 gram ammonium formate use high purity so that you don't have to filter the buffer, and you can weigh it on a top loading balance. And then you transfer all the powder into a 1 liter purified water and mix them well. And then you add about 0.65 ml of formic acid using a disposable pipette tips. And then you basically need to titrate or adjust the pH to 3.8, which is the pKa of formic acid, using high grade of formic acid. So I mentioned that the filtration is not required if you use high purity ammonium formate. Okay, here's topic number 1, the use of balanced absorbance mobile phase for low UV detection monitoring wavelength. This is basically used quite commonly for the assay of peptide and protein using TFA or for other pharmaceutical analysis. This is to prevent gradient baseline shift at low UV detection. You can do that for TFA, formic acid, and other additives which have N absorbance. Here's a chromatogram showing you a gradient analysis using 0.1% TFA. You can see that you have the same amount of TFA in water and 0.1% TFA in the serum nitrate, and you can see a substantial gradient shift. Okay, this might be okay, but it's cosmetically not important. Does not look cosmetically good. And also, a lot of time, if you have peaks which are at the tailing end of the main component, your integration might be compromised. Now, if you look at the UV spectrum of TFA versus water, you can see that there's quite a bit of N absorbance. Now, you might argue that since you're using the same amount of TFA in both water and serum nitrate, you should not have too much N absorbance. However, there is something called the chromophoric shift, meaning that when TFA is exposed in different environment in water or serum nitrate, they have different absorption wavelength, the shift. So, you have some uncompensated absorbance if you use the same amount of level. Also, there's the refractive index not the same. So to lessen the gradient shift phenomena, very common that you see this type of thing going on. You use about 60% of the TFA in mobile phase B. When you do that, you find out that your gradient shift is almost negligible, and this is kind of a very universally adopted, particularly in peptide mappings when you're doing high purity assays. The next topic is the use of high pH mobile phase, which is an option, a very useful option if one want to encounter the analysis of very highly water soluble basic drugs. And when you go to high pH, you can increase the retention and also improve the peak shapes of the basic analytes. Okay, because at low pH, the basic analytes are protonated, so they have no retention. Also, you tend to have higher peak tailing factor for basic analytes. Now, prior to 1990, this use is not universally because there's very few column which is compatible to high pH due to the dissolution of any silica in the silica-based column. So, prior to 1990, you don't see too much of these high pH application for basic drugs. So today, one can use a newer high pH compatible column. Some example are hybrid with bonding chemistry, which is using a more robust bonding chemistry, such as a polyfunctional silane. So it's a very attractive approach for a water-soluble basic drug. One example is the analysis of opioids, like morphine, oxycodone, OxyContin, etc., which are very compatible to this type of assay. So once again, the advantage is good retention, good peak shape, also very much mass spec compatible if you use a volatile additive. It's much more preferable to the use of ion pairing reagents because generally it's not gradient compatible and mass spec compatible. However, one precaution is that many drugs, I would say 5 to 10% of drugs, are not stable under high pH. So the use of acidic pH is the default mobile phase A for pharmaceutical analysis. Also, in some cases, if you go too much above pH 10, some system modification might be needed, such as using a high pH pump seal and using a different injection rotor seal might be needed. Or you might use a biocompatible HPLC system. Here is one references, which I would describe a little bit later. Oh, here's a case study on demonstrating that you can get much better retention. Here we have two drugs, and these are basic drugs, the antidepressant amitriptyline and nortriptyline. And you can see that at low pH with a certain amount of mobile phase B, there's really no retention because these drugs are ionic, they ionize, they are protonated. When you go above 8, which is, 9 is their pKa, and about 8 or 9, 10, then you can see that there's substantial retention. The K is much higher because, the drugs are not now non-ionized. So it's much less ionic or much less polar. Looking at the chromatogram, you can see at pH 2, there's no separation between the two drugs. 8, you have good selectivity, and then at 10, you have much higher retention and higher resolution. Okay, another example, this example came from Waters Corporation, showing the separation of 6 different drugs. Right now, it turned out that most drugs are basic. About 85% of all the small molecule drugs are basic. About 5 to 10% of the drugs are acidic. One example is ibuprofen or Advil, and very few drugs turn out to be neutral, such as acetaminophen or Tylenol. So here are some of the conditions. With the column is an Xtera C18 column. A mobile phase is a different type of buffer at different pH. One can see that in acidic pH, most of the drugs are not well retained. At high pH, all the drugs which are labeled red, 2, 3, 4, and 5, which are basic drugs, at high pH, they are highly retained, right? And they do show a better resolution. pH 5, you can see, there are some more retention. pH 8, the basic drug also retain. So you can see that the retention definitely increases with high pH due to the non-ionization of basic analytes. Mobile phase pH has a dominant effect on the retention of both acidic and basic drug, right? So this is a dominant. Once it get ionized and non-ionized, the retention characteristic is night and day. They are very different. Here's a case study also from Waters Corporation showing you the differences on this separation of these 12 drugs. Once again, 4 of them are labeled red, which are the red is acid and the base is a blue. And you can see for the basic drugs, under high pH, they are very well retained. However, under acidic condition, there's quite a big shift towards lower retention time. The red acidic drugs are just the opposite, right? It's a huge factor. It's very important to, you might not need to buffer it, but it's very important to either acidify or basify when you perform pharmaceutical analysis. Here's another more real-life application, right? So this is published in 2003, demonstrating almost the first use of ICH compliant impurity assay using high pH mobile phases. This is when the columns which are high pH compatible was available in the early 1990s. So this is using this particular column, which is high pH compatible. We're using a bicarbonate, ammonium bicarbonate, pH 9.1 buffer with a acetylnitrile. And shown here is the retention marker solution of two drugs, API A and B. These are opaloid, right? API stands for active pharmaceutical ingredient. And these are the actual expected impurity or degradation product. And here is a critical pair, which is the N-oxide equivalence analog of the API. Yeah, these are the critical pair. Topic 3, which is a pretty important topic on troubleshooting. This is the phenomena called ghost peaks. Okay, ghost peaks are pretty common, and every time you run gradient, you do see towards the end of the gradient some small peak, which are quite normal. But these should be relatively small, perhaps less than 5 milliabsorbent units. Now, occasionally, due to contamination, typically from contamination of trace impurity, which is chromophoric in mobile phase A, every time you use additive, make sure is very highly pure, high purity, and if you have any contamination on it, it will manifest itself in terms of much larger than acceptable ghost peaks. So it is very common that every time we do an assay, we do a blank injection or make a no injection, and we look at the blanked gradient, and it should be a pretty, there should not be a high level of ghost peaks. Now here's one case study from 2013. Okay, so one of the lab analysts experienced excessive amount of ghost peak. It took a lot of time, about a week, to troubleshoot it and to really find out what the root cause is. It turned out that the problems associated with a central laboratory service would do the bottle cleaning. And they actually changed the detergent formulation in their washing machines. And it turned out that the washing cycle does not dissolve all the residual detergent, and that is the cause of excessive ghost peak. Now, once you diagnose the root cause, it is just a matter of rinsing out the solvent reservoirs. Then you basically back to normal. But ghost peak could be very phenomenally problematic occasionally. Another situation, which is actually from my own personal experience on that. Okay, so this is a high pH assay, and one day we experienced a very huge ghost peaks. Now it turned out that when we do the pH adjustment, we do titration, and then it's very customary to dip the pH electrode into the mobile phase A and then keep stirring until you hit the target pH. Now it turned out that even though we always rinse out the electrode, due to the age of the electrode or something wrong with the liquid junction, that there's a little bit of residues left on the pH calibration buffer, right? Now these are different color buffer, and they have a shelf life of about 1 year, and they does not need to be refrigerated. So there's actually a preservative on it, which is called sodium phenolphthaleate. Yeah. So it turned out that for whatever reason, the electrode is not totally clean, and when you dip it into your mobile phase A, there's trace amount of these preservative, which manifests itself as a ghost peak. This ghost peak is substantial. It's about almost 30% of my reference standard, which is 100%. So this is clearly something that is not acceptable. So the solution that we adopted later on is we do not dip the pH electrode into mobile phase A, just completely not do that during the pH adjustment for mobile phase A. And basically we would do titration, and add more acid or base, and just remove an aliquot, let's say 3 mil aliquot, during the pH measurement into a separate vial, such as a scintillation vial, and just check the pH that way. And we don't pour back. We just wasted whatever is being titrated. Okay, some comment on shelf life and also reagent quality. So the purity of the solvents are very important to reduce operation issues, such as particulate, ghost peaks, UV transparency, are particularly problematic at low UV detection. And this is actually more important at low UV, that you have more problems with the use of some of these newer detectors, such as ELSD, evaporative light scattering detector, charged aerosol detector, and mass spec detection, right? So the reagent purity is much more significant than just regular detection UV at lambda max. Comment on the shelf life. I would just say that the actual shelf life of mobile phase is really not an exact science, right? It's really difficult to ascertain when is it not acceptable shelf life, right? You can see that if you have a mobile phase aqueous buffer, they do support bacterial growth or algae growth, right? So shelf life of aqueous mobile phase is more limited because of potential for bacterial algae growth, particularly for ammonium buffers at more neutral pH. So here are some of the guesstimates. Okay, so buffer probably would have a shelf life about a week or so, 2 to 3 weeks if refrigerated. And obviously, you do not expose the buffer to direct sunlight. For simple acidic mobile phases, such as 0.1% formic acid or TFA, 2 to 3 months is definitely okay. And for organic mobile phases, I would say at least 6 months. The exceptions is THF. Topic number 4 is on the use of TFA, which is very common on reverse phase separation of protein and peptide. And also we do LCMS analysis of protein and peptide. Now TFA is preferred because it gives you very good peak shapes, very sharp peaks, because it's a it is a ion pairing reagent, right? It pairs the ions, make it a neutral ion pair, and therefore you have better peak shapes and also more retention. This is great. Unfortunately, TFA, because it's an ion pair reagent, would suppress ionization in the mass spec. So the signal is compromised. So what can you do, right? So the proposed replacement, if you want to have both mass spec and good peak shape and mass spec signal, is to use a newer additive called DFA, difluoroacetic acid, give you the best of both worlds. Another one is 3-FPA or 3-fluoropropionic acid. This is work done primarily by Barry Boyles of AMT, right? So published in 2018 in this white paper. Here are some case study, right? You can see if you use formic acid, you have good signal in mass spec, but the peak shapes are not good, right? DFA, you have the best of both worlds. You have pretty good mass spec signal. TFA, not the signal are suppressed. And another one is, which is pretty good, is the mixture of formic acid and ammonium formates. So DFA used good peak shapes with less ionization suppressions under ESI, electrospray mass spec interface for protein and peptides. Okay, another case study. This is using peptide mapping, right? Peptide mapping is highly used in modern de novo sequencing of protein using either QTOF or OB traps. So you can see that the 10 millimolar DFA give you good peptide maps, while TFA almost no signal. And the formic acid is good signal, but peak shapes are not highly desirable. Okay, another case study showing, on some of these peaks that, you can see really poor peak shapes with formic acid. And DFA, give you as good a peak shape as TFA. Okay, topic number 5 is on the use of ion pairing reagent. Want to mention the ion pairing reagent often used in traditional older HPLC method for the increased retention of under reverse phase condition, particularly for basic drug or basic analytes. Ion pairing works because they are like a detergent. They will pair ion with acid or base to give you a neutral ion, therefore increasing retention under reverse phase. Okay, it's very common to use an alkyl sulfonate, such as, in this case, sodium hexylsulfonate, common ion pairing reagent in method, particularly for methods such as water-soluble vitamin, very common. Okay, so these are kind of problematic because they're not really these longer ion pairing reagent are not kind of gradient compatible. It takes a long time to equilibrate, and also not mass spec compatible. A notable exception is the modern use of some newer mass spec compatible ion pairing reagent, such as HFIP, hexafluoroisopropanol. So here some, particularly in the separation of oligonucleotide, which is becoming a very important new drug modality. Shown here is oligonucleotide using this mixture of triethylammonium and HFIP reagent to give you very good control on the separation of single-stranded or double-stranded DNA oligonucleotides. Another important, nice topic is the use of chaotropics reagents in reverse phase chromatography. So what are chaotropes or chaotropic reagents? They are polyvalent ion, such as PF6, BF4, borate, and also perchlorate ion. These are polyvalent ion, which kind of break up the water tension, and then it's a good additive to increase retention and give you better selectivity of any basic analytes, which otherwise would not be retained under reverse phase. They also tend to improve pigtailing for the analysis of compounds such as proteins, detergents, and antibiotics, such as penicillin. So these are some of the structures. So chaotropes are better suited for gradient analysis and produce a lower baseline shift, than the ion pairing reagent, which are more traditional ion pairing reagents. Okay, a couple other mention of things that's notable, which is the use of phosphoric acid and the use of MTBE, which stands for methyl butyl ether. Now, in my opinion, the use of phosphoric acid is underutilized, meaning that people should really use it more because it is a very good additive. It's very strong acid, and it's totally transparent down to 200 or 190. So people tend to use phosphate buffer, which is a little painful to prepare, right? So phosphoric acid is much easier, and it's good for purity assay methods for raw material or starting material. Unfortunately, obviously, phosphoric acid is not mass spec compatible. Okay, we commented THF actually have some, it's good for selectivity, but it is very toxic. It's something not recommended in general use, except for GPC. However, there's a pretty nice substitute called TBU ether, right? So it's also an ether, but it's much less toxic. However, for some, it is not totally miscible with water, so you cannot use too much of it because it's not miscible. And it does not form peroxide. It's much less toxic. So a small amount of MTBE instead of THF will give you some selectivity effects. So here's my summary of some of the best practices and recommendation on the selection of mobile phase A and B. For mobile phase A, we can see a clear trend of the increased use of mass spec compatible buffer. However, at much lower concentration, I think some of the older trends is using 50 millimolar phosphate buffer, right? So just everybody kind of keep using that. It's way overused. Also, using something called the balance absorbance mobile phase, using different amount of TFA or formic acid in A and B, a reduced amount of mobile phase B. The use of high pH mobile phases for the retention of water-soluble basic compounds and basic drugs. More reduced use of non-volatile ion-pairing reagents and Chaotropes. We say that the use of phosphoric acid is underutilized, and actually in a lot of cases can replace using a phosphate buffer. And mobile phase B, definitely prefer use of acetonitrile for better separation efficiency, for better UV sensitivity, for actually higher column efficiency, and particularly for wavelength lower than 220 nanometers. Here are my references, some of these recommended references. The one in red are the one probably would be the more useful. For more information, you'll refer to the website and also to be a subscription to the channels. Here is the quiz for episode number 5. First one is which mobile phase require filtration, and most of them might not require filtration. Number 2, some balance absorbance mobile phases. 3 is sample type is applicable to high pH mobile phase. Next is one on ghost peaks, and then the LC mass spec of protein and peptide. On that note, thank you for your attention, and we see you next time. I hope you enjoyed this video. Please subscribe for other HPLC topics and leave me comments or questions. Connect me on LinkedIn and also visit my website for other resources. See you next time.